Generating a faster response from LLM has always been a huge task, and every one of us needs our LLM model to generate a quicker response. We need a faster inference. This is where we have vLLM, which is an efficient memory management for large language model serving with page retention. So talking about page retention, there are been a various methodology using which you can generate a faster response. We had distributed KV caching previously, but there was always an issue of memory thing when it comes to distributed KV caching. This is where page retention comes into the picture. And there is this beautiful article which is written by Astrang, which is on vLLM, a faster inference pipeline for LLMs paper explained. So this will give you a wide picture on what are the limitation with KV caching and what is different in page retention. So page retention is the major technique, I'll say, using which vLLM can generate a faster inference response along with memory efficiency. And you can check out this article. I'll link this article in the description, and it will give you a wider picture of how attention plays a vital role in the transformers. So let's get to the code implementation. In this particular code implementation, we will do inference on two different models. Since we are using T4 GPU, obviously we have limitation. But if you are using V100 or A100 GPUs, you can use any 7 billion parameter or 13 billion parameter large language model. In our case, we'll be using 5 billion parameter model and 2 billion parameter model to give you understanding of how you can use vLLM for faster inference. So the first step is pretty obvious. You just have to run pip install vLLM. And then there are two models that we will be using. First, we will look into Gemma, which is a 2 billion parameter model by Google. And then you have Camel 5 billion parameter model by Writer. So let's quickly get started with the code. And as you can see, we have already run the code. Usually in my playlist, we write code live. But since model loading takes time while you're doing the live coding, that's the reason why we'll directly explain each line of code. So as you can see, the tick mark has gone. But if you look at the tick mark, which is the cell execution, it is visible in the Camel-5B. I'll tell you the reason why it is visible here and why it is not visible here. All right. So in order to get started, the first step is you need to run pip install vLLM. And after you install vLLM, you need to add your HF token. So in order to get your HF token, you just have to go to huggingface.co. I'll show you the website, huggingface.co, settings and token. So you need to create a new token over here. You just have to copy it. If not, we'll generate a new token. You can write vLLM Inference, and you can keep your role to be right, and you can generate a new token. Just copy this token, come back to your VS Code, not VS Code, rather Collab Notebook. I have a practice of telling VS Code because I use it a lot. And you just have to paste your key and log in. So once you paste your key, it should show you login successfully. The reason why we need to add access token is because Google Gemma model can't be used directly. It requires you to add your access token. That's the reason why you need to paste your access token by using from Hugging Face app, import notebook login, and notebook login, you need to call that function. Cool. Now you just have to use two different libraries. One is Torch, which is PyTorch, and then vLLM. From vLLM, there are two things that we need to use. One is your LLM, and one more is your sampling parameters, params. So the sampling params is nothing but whatever we give in Hugging Face pipeline, right? Repetitive token, repetitive penalty, temperature value, top K, top V, all these values, you need to assign it with sampling params. And LLM is where you can directly import your Hugging Face model repo and it will execute it. And these are the two libraries that we need to use. OS is mainly used to get the number of devices, how many GPUs you have. So let's run this as well. So as you can see, we'll probably have just one because Collab Notebook doesn't support multiple GPUs. So when I run this, it will show me one. But if you are using Kaggle models where you have 2x T4 GPU. If you run this particular line, you will get 2. The reason why we are using this parallelism is so that we can have model parallelism in our code approach. This doesn't make sense in Colab Notebook because you just have one. But if you are using Kaggle, make sure you execute it and you have your hardware accelerator to be T4 GPU, which provides 2 GPUs. And once you have this, you need to run this particular statement. I won't run this line because it will take time to download my model. So as you can see, we just have to use LLM. From LLM, your first parameter will be Google/Gemma 2 billion parameter. And then you need to assign your tensor parallel size, whatever you have executed from your OS environment devices. And once you do this, there are 2 ways you can execute this. One is if you don't have A100s, you need to use torch.float16. If you are using A100 GPU, you can make sure to change this value into torch.vFloat16. So since we have T4 GPU, I'll be using torch.float16. And once you define these 3 parameters, you can run this code. And there is one more approach that you can take. Suppose you have a quantization model, you can choose AWQ quantization and you can look into the documentation. It's just one additional line, your one additional parameter, and you just have to update this particular model, which has AWQ quantization. So since we're not working on quantization, these are the 3 parameters as of now. And once this is done, you need to free up little bit of RAM by using torch.cuda.empty cache, because you are gonna utilize RAM memory when you are loading a model. So as you can see, we are able to load the model. It will download your token config.json and model safe tensors. In some case, it will be bin, because there are 2 files approach. One, either it will be safe tensors, either it will be bin. And once the model is downloaded, you need to empty the caching. And this is what I was talking about. There are different parameters that you need to add when you have to get certain response. One is your max token. If you give max token to be 100, your response will be very less. That is your maximum response limit. If your maximum response limit is 512, it is very negligible and it suffice of whatever use case you're building. And there are multiple chances whenever you use 5 billion parameter, 2 billion parameter model, the repetition of the text will happen. If you want to avoid the repetition of the response, you need to give a higher penalty, which is your repetition penalty to be 1.1. It should be very close to 1. Don't give it very less than 1. If not, again, you will get few limit repetition in the response. And temperature, since we are not providing any document here, we can have our model to be very creative. That's why I have given a larger value. And top P penalty, I've just given it to be 0.5, which is very close to 1 and 0. And now once you add your sampling parameters, you just have to run your LLM.generate. Here you need to add your prompt. Along with your prompt, you need to add your parameters. These parameters are very similar to Hugging Face pipeline, as I mentioned earlier. So once you execute this, as you can see, I've just run what is ML. The major thing what you need to notice in this line is this particular time. It just took 1.7 seconds to execute a 2 billion parameter model in a Colab notebook, which is very rare, because if you are executing this via Hugging Face pipeline, it's gonna take at least a minute to generate a response. But as you can see, with help of PagedAttention, that is your vLLM, you're able to get a faster inference. This is where vLLM is best. And then you just have to return your response. So this is your response. ML stands for machine learning. It is a branch of computer science. And you're getting a decent response from a 2 billion parameter model, which is good. And then again, let's do the caching part. We'll remove a little bit of RAM and we'll create a space for our execution of the model. This is the first approach of using a Gemma model, which is a 2 billion parameter. And now we will look into the response, how the response looks like, what are the different things that a model will generate. That's where you need to restart your runtime again, because we'll be using a different model now. The different model that we will be using is Camel-5B, which is an Hugging Face model by Writer. And here, if you can see, I'm able to execute all these things. So what I did, right? First, I wrote this code. First, I wrote this code of Gemma, and then I click on runtime, and I will restart the session so that you can use two different model in the same collab notebook. If not, you have to create two collab notebook, and there are few limitations that you can't get your T4 GPU every time. That's where I use the same collab notebook so that I can show you the demonstration of both the models. So here we'll run the model, we'll run each line of code. So first step is very simple. We use import OS, as I said earlier, to get the device name, and vLLM for our importing or loading our model from Hugging Face and sampling parameters. We'll set up our tensor parallel size and torch.CUDA to free up the space. I won't run this line because I've already loaded the model. As you can see, it is already utilizing my disk space. So you can see the RAM that I have. I've already touched the limit. I only have 15 GB and I've utilized 16.6 GB, almost 14 GB. And disk space is also full. System RAM is almost full as well. That's the reason why I'm not running this line of code, which is my LLM. And this is very self-explanatory. Import your repo ID and then add your parallelism. If you have multiple GPUs, this is gonna be very efficient. If you don't have multiple GPUs, even that is fine. You can just add one. And then D type, if you're using A100, use B float. If not, just use float 16 floating representation. And once you run this, here we need to play around with the max tokens, which is your 512. I'll remove this parameter so that you will be able to see there are times when the response will be repeated. I'll run this. And here my temperature is 0.1 and my LLM2.generate, I'm adding a prompt saying describe a futuristic device that revolutionize space travel. And then you need to add your parameters, which is your temperature, max tokens, repetitive penalty, top P, top K, so and so. And once you run this, right, as you can see, it will only take you around less than 5 seconds. So as you can see, it just took 1.6 seconds. That's where vLLM is very fast. And now if I print this response, it's not repeating, that is good, but it's really very efficient to use repetitive penalty to be 1.1. And what do we have in the response? I'll just print response. All right. So the first thing is you have your prompt and then you have prompt tokens. Since vLLM internally will do the tokenization of your LLM model, referring to whatever repo ID you give. So each prompt will have its own ID. And once you have its ID, you're also getting the text. So this is what our response should look like. So what do we need to do? Once you print the response, it is a list. That's where you need to get the 0th index. In the 0th index, you have this parameter called outputs. And inside outputs, again, you have a list. And inside list, in your 0th index, this is my 0th index. Inside my 0th index, I need to extract my text. And that's what we are doing here. Response, 0th index, output, 0th index, and text. This is my result. So this is it from this video. And the major thing that I wanted to share is you can run your LLM pretty fast using vLLM, and you can play around with different parameters. You can play around with quantization, and you can look into the documentation part. But before we leave, if you want to dive more technical enough to understand what KV caching is and how paged attention comes into the picture, you can read this article over here. And it's very neatly written, and it's the best what I could have find when it comes to vLLM resources. And I will attach this link in the description. And if you are really keen enough, you can also read the paper, and you will find the paper link in this blog article as well. Do subscribe. We'll come up with more videos very soon.